The universal relation. Hello, everyone. As we begin our lesson on relations, it is important to note that we often encounter certain types of relations that are described as trivial. In a mathematical context, trivial doesn't mean they are unimportant. Instead, it means they represent the extreme boundaries of how elements within a set can be connected, essentially the simplest or most absolute cases possible. One such example of these extreme boundaries is what we call the universal relation, which is the primary focus of today's session. In the following slides, we will define exactly what this relation is and look at how to construct it. Understanding the concept. Now that we have introduced the idea of trivial relations, let's dive deeper into the actual concept of the universal relation. First, let's look at the formal definition. We say that a relation R on a set A is called a universal relation if every single element of set A is related to every single element of set A, and this crucially includes each element being related to itself. To put this in simpler terms, if you are working with a set A universal relation is one where no element is left out and no possible connection between any two elements is missing. It is the most inclusive type of relation you can have. Essentially, this means that every possible pairing that can be formed using the elements of set A is present in the relation. In the next slide, we will explore how to represent this mathematically using the Cartesian product. But for now, just visualize it as a complete web of connections where everyone is linked to everyone. Mathematical representation. Now that we have a conceptual understanding of what a universal relation is, let us look at how we express this formally using mathematical language. To do this, we rely on a fundamental concept known as the Cartesian product. When we speak of the Cartesian product of a set A with itself, which is denoted as a cross A, we are referring to the set of all possible ordered pairs, a comma B, where both A and B are members of set A. Therefore, we can define our topic precisely. A relation R on set A is a universal relation if R is equal to a cross A. Because this relation R contains every single possible pairing that can be formed from the set, it is the largest possible relation that can be defined on any given set A in the next slide. I will guide you through a step-by-step process to actually construct one of these relations. Step-by-step construction of a universal relation. Now that we have established the mathematical definition and the concept of the Cartesian product, let us move on to a practical visualization of how a universal relation is actually constructed. To do this, we can follow a simple four-step process. First, in step 1, we define our set, which we will call set A. Step 2 is straightforward. We identify every single element that exists within set A. In step 3, we perform the core action of the universal relation. We form every possible ordered pair, x, y, such that both x and y belong to set A. This means we are pairing every element with every other element in the set, as well as pairing each element with itself. Finally, in step 4, we include all of these generated pairs into our relation, R. To make this process clearer, let us look at a concrete example. Suppose we have a set A that contains the elements 1 and 2. As we can see, the elements are simply 1 and 2. Now we apply step 3 and form all possible ordered pairs. First, we pair 1 with itself to get 1, 1. Then, we pair 1 with 2 to get 1, 2. Next, we pair 2 with 1 to get 2, 1, and finally, we pair 2 with itself to get 2, 2. Thus, the universal relation R is the set containing all these pairs, 1, 1, 1, 2, 2, 1, and 2, 2. As you can observe, every possible combination has been included, leaving no element unconnected. In the next slide, we will see how this mathematical structure translates into a real-world scenario. Real-world example. Now that we have seen how to construct a universal relation using numbers, let us apply this concept to a real-world scenario to make it more intuitive. Imagine we have a small group of students in a classroom. We can represent this as set S, which consists of Alice, Bob, and Charlie. Now let us define a relation, which we will call relation R, as is in the same classroom as. To understand how this works, let us break down the connections. Since all three students are in the same room, Alice is in the same classroom as herself, as well as Bob and Charlie. Similarly, Bob is in the same classroom as Alice, himself, and Charlie. And finally, Charlie is in the same classroom as Alice, Bob, and himself. Because every single student in our set is related to every other student, and crucially, to themselves, this relation R is a universal relation. Mathematically, we express this by saying that relation R equals the Cartesian product of set S cross set S. This confirms that every possible pairing has been made, which is the very definition of the universal relation we have been discussing. Key takeaways. Now that we have walked through the theoretical definition and seen a practical example with the students in a classroom, let us summarize the key takeaways to ensure the concept is clear. First, let's revisit the definition. A universal relation is one where every single element of set A is related to every single element of set A, leaving no pair unconnected. In terms of the mathematical formula, we express this as R equals across A, as we discussed in the earlier slides. This means the relation is identical to the Cartesian product of the set with itself. Regarding its nature, you will often hear this referred to as a trivial relation. It is called trivial because it provides no specific or distinguishing information about the elements. It simply connects everything to everything else without any special conditions or restrictions. Finally, in terms of scope, the universal relation represents the maximum possible relation that can be defined on any given set. Since it contains every possible ordered pair, it is impossible to create a relation larger than this. Now, while this concept is straightforward, it is common for students to confuse it with other types of relations, so let us move to the next slide to discuss some common mistakes to avoid. Common mistakes. Now that we have covered the definition and the construction of the universal relation, let us move on to some common pitfalls. It is important to address these to ensure you have a precise understanding of the concept. First, students often confuse the universal relation with the identity relation. While they may sound similar, they are fundamentally different in scope. In an identity relation, an element is related only to itself. In other words, the relation consists of ordered pairs where the first element is A and the second element is also A for every element A belonging to set A. In contrast, as we have established in the previous slides, a universal relation is all-encompassing. Here, an element is related to every single member of the set, including itself. This is why we define it as the Cartesian product, across A. To illustrate this difference, let us consider a set containing the elements 1 and 2. The identity relation would only include the pairs 1, 1 and 2, 2. However, the universal relation is much larger, containing all possible combinations: 1, 1, 1, 2, 2, 1, and 2, 2. The second common mistake is ignoring the self-relation. Some beginners forget that for a relation to be truly universal, every element must be related to itself. For instance, the pair a, must be present for every element in the set. Keep in mind that if any of these self-pairs are missing, the relation is not the complete Cartesian product of across A, and therefore, it cannot be classified as a universal relation.